Hi everyone, welcome to new video from Nitinol Engineering. This is the fourth part in the series Shape Memory Alloy Modeling using Finite Element Analysis. If you did not see last 3 videos, please take a look at them first. You will find all the links in the description box below. In this video, we are going to focus on solving example of bending orthodontic arc wire using thermomechanical model of shape memory alloy in Marc Mentat. Before we begin, quick recap of what we saw. We discussed a shape memory alloy is a metallic material which can be bent in any form plastically, and then when we heat that material, it will go back to its original form. This unique property of shape memory alloy is a consequence of reversible solid-solid phase transformation, and this phase transformation can occur because of stress or temperature. At low temperature, we have martensite phase which can be plastically deformed, and on heating, martensite will get transformed to austenite, causing the part to go back to its original shape, and after cooling, that shape will be retained. Now, because of this, SMAs have two key characteristics. One is shape memory effect, which we just discussed, and another is super elasticity. In super elasticity, there is no temperature change because the working temperature itself is high, so material is always in austenite phase. When it undergoes large deformation, because of stress, austenite converts to martensite, and when load is removed, again martensite gets converted back to austenite, which results part going back to its original shape. And we discussed some applications of SMAs as well. In Marc, we have 3 material models to simulate SMAs. These 2 models are thermostructural, and this model is only structural. We already discussed thermostructural models and solved this example where this 3D bar is fixed at one end and we are just cooling it down and again heating it. As you can see in previous example, there was no stress involved, but now we are going to solve this example. This is the original shape of wire. It is fixed over here, and we are going to apply displacement boundary condition on this end. This figure over here shows the entire geometry of orthodontic wire, but because of symmetry, we are not considering half part of it, and we will simulate only this part. The displacement is applied in X direction, and this table over here shows how the displacement is going to change. So we are going to linearly increase the displacement and then again bring that to 0. If we plot this loading cycle on stress versus temperature diagram, it will come as a vertical line because now there is no temperature change. In earlier example, it was horizontal line, but now it is vertical line. And the location of this line will depend at what temperature we are simulating this. In this example, we will simulate at 2 temperatures. One is 35 degree and another is 5 degrees. 35 degree is the temperature which is higher than AF0. So at 35, material will be in austenite phase. Once we apply loading, we should see austenite getting converted to martensite, and again as we unload, martensite will get converted back to austenite. Let's start with Mentat. I'm not going to start the model from scratch because that is something we already saw in earlier video, and another reason being this model is already available in Mentat. You just have to go to help, go to users guide, and over here search for shape memory alloys. This is example number 52. You can find all the details over here as well. And if you just scroll down, then you have a procedure file over here. All you need to do is just click on this play button and you will reach to this point. Anyway, so let's see what we have here. I'm going to expand all the folders. Of course, we have this wire. Then let's go to boundary conditions and see what boundary conditions we have. On the top, we have fixed symmetry boundary condition, and on this end, we have displacement boundary condition. Just to make sure if everything is correct, open this. And you can see we have displacement in X direction of 5 mm, and we are using this table for the displacement. That table can be found over here. This is the table where we are increasing the displacement and again decreasing it. Go back to model. We are also restricting that wire to move in Z direction. That's why this displacement Z is 0. Then the temperature is defined over here in state variable element temperature. You can see right now it is 35 degrees. Next, let's see the material card. We are using thermostructural model. Elastic properties of austenite and martensite are provided here. We have thermal coefficient of expansion as well. But in this example, temperature is not changing, so this is not going to play any part. We have plasticity defined over here. The transformation temperatures are over here. Initially, we are starting with 0 volume fraction of martensite. Hence, entire part is austenite. Transformation temperatures for austenite. And finally, the G function. Say OK. 2 load cases are defined. First 1 second, and here both boundary conditions will be active, and similarly another 1 second, here also both boundary conditions will be active. We can define it within one single load case as well. This is just to maintain the loading and unloading separately. Then job is created, both load cases are selected, there is an initial load where we are selecting this temperature as well. And in job results, we are asking for volume fraction of martensite and equivalent von Mises stress. Say okay. Let's go to run and submit the job. Let's open the results. First, let's see stresses. For that, I'm going to change this to contour bands and here von Mises stress. Now as we start loading, you can see stress concentration is happening over here and here. And once we go to 100, I think our loading will be complete. This is the maximum loading. And after this, there will be unloading. If we see the martensite volume fraction, initially everything is austenite. So martensite volume fraction is 0. But as stresses increases, you can see martensite forming over here in the highly stressed area. Let's go to 100. And now we see most of the austenite converted to martensite. Let's start the unloading. And after unloading, again we are back to austenite. That is because if you see the location of this vertical line, we are doing this cycle now, which is at 35 degrees. When we do unloading, at this stress level, conversion from martensite to austenite starts. And over here, it is completed. Hence, when unloading is complete, we get almost 100% austenite. Now, what will happen if we shift this line towards left? And how we can shift that is, we just have to change the temperature. And we will bring that to this temperature over here. That means austenite conversion should not start. So to do that, I'm going to close this. And over here, we just have to change this to 5. That's it. And run the job again. Let's see if we got different volume fraction of martensite. Loading, it should be same. Here the larger portion of wire got converted to martensite because we shifted the loading line towards left. Now when we do unloading, we can see martensite was not converted back to austenite as we did not cross these red lines. One interesting thing to note over here is now temperature did not change. So we don't need thermal analysis in this. We don't have to solve heat equation. Only mechanical analysis is enough. Therefore, when our application doesn't involve temperature change and this vertical line is on the right side of this AF, so basically this area over here, then we can simplify the constitutive model by a huge margin. Like number of parameters also can decrease a lot, which is exactly what is done in Marc. And for that, we have another constitutive model, which is only structural model. That's going to be the topic of next video. After this, we have only one more video coming in this series. And in that video, we are going to discuss in detail what is only mechanical model, which is used to simulate super elasticity in Marc Mentat. And we will also solve the same example using that model. If you like this video, please show your support by subscribing to this channel, which will give me motivation to create more educational videos like these. You can also go to channel's playlist tab and here you can see all the videos with similar topics combined together. For example, let's say if you're interested in ANSYS tutorials, you can go to this ANSYS tutorial playlist and see all the videos from this playlist. All the codes and files which I use for these videos are also available for you to directly download from this channel's GitHub profile. The link of this profile is given in the description box below. If you have any questions, please let me know in the comment section below. And as always, thank you for watching.